So the Riemann sum is something actually from calculus. And there's also a text cell, well, actually, it's code cell of hint, sort of giving you an idea of what we are expecting. Um, okay, I don't have the notebook in here, so let me put it in the Q&A part. Right. Um, okay, so what are we expecting? So we want to write a loop that gets the nth left-hand Riemann sum of the function f of x equal to x squared on the interval from 0 to 1. So if you're looking at the sum right here, this is sort of what you are expected to compute, because essentially this is dividing up the interval from 0 to 1 into n pieces. So let me see if I can copy these lines so that I can put them in the well, probably not. Okay, so yeah, let's just directly write it in the screen. So you have what? You have f of x equal to x squared on the interval from 0 to 1. You want to do n subdivision and left hand Riemann sum. If I remember correctly. So essentially the idea is that, okay, I have an interval from 0 to 1. My function is a quadratic, and well, it should be a dashed line. So it's a 1 here. Okay. So when you try to do the Riemann sum, essentially you are trying to look for the area under the curve, right? So now if you want to divide it up into, let's say, 4 pieces, what do? So it's going to be evenly subdivide the domain interval into from 0 to 1 over 4, from 1 over 4 to 2 over 4, and from 4 over 4 to 3 over 4, and 3 over 4 to 1. And then if you're using the left hand Riemann sum, essentially you're saying, okay, every subinterval, I'm going to pick the left endpoint to get the height of the rectangle. On the left end is always a 0, so fortunately there's no area. And then the one on the left is this one. The one on the left is this one. The one on the left is this one. Okay. So essentially, what are you summing? You're summing 1 over 4 times, now the first left endpoint is 0 squared, plus now the second one is 1/4 squared, then 2/4 squared, and then 3/4 squared. So that's the area under the curve, but approximated using the left rectangles. So you can think about, in general, you're gonna subdivide the domain from 0 to 1 into n equal pieces, right? And then each sum. So I'm gonna write a sigma notation for the summation that you may be familiar with from calculus 2. So essentially, you're gonna have k from uh, so let's just use the indices from 0 to n, n minus 1. Okay, so just like what you see in Python. So you have basically you're looking at the left endpoint. Remember the left endpoints there, what they're from k n over k to n over, excuse me, k over n to k plus 1 over n. Okay, so the length of each one is indeed 1 over n. And then that's the kth, right? Wait, that's the interval, subinterval with index k. And of course, k goes from 0 all the way to n minus 1. Right? And then you are looking at what? You're looking at the left rectangles. Okay. So then this is going to be the sum of k over n whole thing squared. And of course, there's nothing for the first rectangle, right? So essentially, if you want to sum from k equal to 1 all the way up to n minus 1, that's totally fine. But essentially, you are computing this. So, so far, does it make sense? So that's I think we have a relatively common issue, but not universal. So
Load that thing on one, please.
that's on OneNote. Yeah, this
is-
this is on the Q&A section. So that's edible from the student's perspective.
Okay.
Yeah. Yeah, so let me mention this is problem set 2, exercise 3. So that's that left hand Riemann sum. So yeah, so this is the Riemann sum with n equal to 3. We are using 3 sub intervals. We have length of 1 over 3 universal, right? But then we have 0 over 3 squared, which is 0. Then 1 over 3 squared, that's 1/9, and 2 over 3 squared, that's 4/9. So that's sort of like a hint. And indeed, eventually you compute up to the 10 subintervals, and you are matching with 0.285. The error should be at most 0.01. Okay, so sort of like that. Okay, this question. Well, I think we don't have a lot of issues here, but I think I updated the class notebook so that I enclosed the lecture 3 live coding session. So you can basically the thing here is that you can start with some guess value and then just approximate the 3 roots, right? You know this is degree 3 polynomial, so there are at most 3 roots. Either it's going to be 3 or you have 2, but one of those is repeated, or you have only 1 and no repetition. Okay, so basically the idea usually is that okay, you start from relatively negative value to get the smallest possible, and you get a large guess. Okay, so basically if you have x value large, then this cubic expression will be rather positive, right? If you have really negative x, then the cube may dominate the rest of the term, so it may be really negative. So from those starting points, you'll be able to approximate the biggest root and the smallest root, or I can say the most positive root and the most negative root. And then if there's a third one, then that's going to be cut in between. So you will be able to eventually, if you're writing your own code, right? You may want to think about it in a more systematic way. So I get the largest, I get the smallest, and then I try some value in between and to get the middle solution. Okay, the third one. So that's there's one implementation that I wrote in the class notebook. So just to mention that we are in the collaboration space. Okay, so that's the page that I added here. So now for the notes, we can look at this part. So yeah, so I think in the discussion from last time, we said, okay, you can predetermine your left bounds, right bounds, and then you can do the iterated steps. That's totally fine. So feel free to modify the code whatever way that you want to make it more efficient. But then when you want to do this kind of approximation, you could do something like this, saying I have also you can try to use one body of recursion All right. So the recursion is always the same. So whenever the functional value is larger than epsilon or less than negative epsilon, then we continue running until the value is less than or equal to epsilon, right? So the body of recursion or yeah, well, you can say the recursion, or you can say the trajectory of your solution sequence. The procedure is the same. It's just Newton's method. But then the gas value, you can think about smart ways to condense the three procedures into one. That's totally optional. But basically, try the right end solution. Let's start with, let's say, 10. The left end solution, let's start with, let's say, negative 10. And then if they are not equal, then you are sure that there's one more, which is in the middle. So then we can use the midpoint of the prior procedures, okay, to automatically calculate the middle solution. So that's a way that can make it a little bit more automated, okay. And of course, you can get more automated up to your particular design. All right, and eventually it just also gives you, okay, upon 8 iterations, I am gonna get the most negative solution, which is a negative 0.260. Upon 6 iterations, well, you see the convergence is pretty fast, right? So upon 6 guesses, I would get the largest solution, which is approximately 9, and the midpoint is 0.8, roughly speaking. But you only need 1 iteration to converge. So yeah, well, this is basically the more ground knowledge that you have for the problem, the more you can make this code evolve, right? So for degree 3 polynomial, the shape is gonna look like what, right? So for instance, it could be strictly increasing, then okay, there's always one solution. But then if it goes up and down, then it's possible that you have a tangent, then there's a repeated root, or you have something like this, okay? There's gonna be a large one, there's gonna be a smaller one, and there's gonna be a one in the middle. And then also still, it's possible that there's only one root. So it's really up to the knowledge that you have. Then you can make the procedure more and more automated rather than guessing. So that's just a thought. So well, yeah, well, eventually the more computational experience that you do, the more you would like to make the things automated. Otherwise, you would have to go back to look at your code every time you run certain experiments, which is a little bit of a pain. So you would also want to make the program print certain things so that, okay, whenever you have something that you wanted to tell you, then just let it do automatically. Okay. Right. So yeah, so that's pretty much, yeah, that's pretty much about what we need to talk about for the homework. So let me quickly just confirm. Oh, question 5. I think this one we did it pretty well. So basically, we assume that we have a number of lists that have the same length, and we calculate the average of all those lists. So essentially, it's a loop which is not really challenging. Exercise 6. So later we're gonna revisit this construction of permutations. So indeed, there are ways that you are able to do it. One way is that you do it sort of like a brute force. So you start with one element, and then what about the next element? For the permutation, you can put it in the front of the before the first element, or put it after the first element. That will give you the permutation of 2. And then for the third element, you would want to stack it into before the first, between the first and second, and then after the third. So indeed, it can be a systematic procedure that you utilizes for loop. That's one way. Another way is that I think many of the submissions are doing the recursion. Okay, so you take one element, and then for the rest you do the permutation, and then put that element at every location that's possible, right? So that's so these are all practical solutions. But one thing we would explore in the future is that, okay, so if you think about permutations, not every list will give you 24 permutations, even though the list has 4 elements. So to be specific, if I have 1117, then you don't really permute 111. So there's only 7 that has 4 different places that will give you only 4 different permutations. So essentially, if you are doing 24 copies of the list of permutations, then there's going to be a lot of repetitions. So those are the things that you eventually would have to think about once you have more domain knowledge. Okay, but that's actually easy to handle. So essentially, you're just saying, okay, I make the list. So basically, I'm now talking about the high level idea that I think later there's going to be a live exercise that you guys can implement. But basically, if I have, let's say, 4, 2, 2, 7, then of course 2 and 2 they repeat, right? But then you sort of have like a decreasing and then increasing kind of behavior of the sequence. Then you may want to sort it, and then whatever you have the element equal to the previous, then you don't do that element for following recursion because it's already done for the prior element. So those are the things that you want to think about. Okay, the more you play with this coding, the more proficient it will become. So any questions regarding homeworks and other stuff? All right, very good. So let's continue with. Let's continue with section 6.
Your quiz coming up soon.
The exam is, let me see. There's going to be an exam on the 11th. Yeah, we do. So so basically the exam will cover what we finish on Wednesday. But I would say the focus will be more about the prior things that we discussed, and the style will be really similar to the quiz. It's just going to be a little bit longer.
It's pen and paper.
Yeah. So yeah, it's sort of like I'm gonna design a notebook, and I may have some errors within certain implementations I want you to point out, or there will be procedures that are not really complicated, but then I would ask you to predict the output. There may be certain blocks of code that you have seen, but then I may hide certain lines and then ask you to fill it out to eventually fulfill certain tasks. Okay, so those are the types that you may see.
So it's from lecture 3 to lecture 6.
Yeah. Well, this is a midterm, so you can think about everything up to lecture 6.
Okay.
So yeah, I think today and tomorrow and Wednesday we should be able to finish lecture 6 and talk a little bit about lecture 7. So yeah, lecture 6 is actually not too bad. All right, let's continue. What's electricity? Mm, yeah, well, we probably should start with the nodes. But yeah, that's fine. So basically, we want to talk about a little bit more on different data types. So let's zoom up a little. So we were talking about lists, right? So basically, lists are using square brackets, okay, to basically keeping elements with indices from 0 up to the length of your list, -1. So, and then the elements could be what? Could be numbers, could be other data types like Boolean and even strings, right? But then we also need to talk about what's called tuple. Uh, and sometimes people call it tuple. Well, it's those are common pronunciations. Sets. So that's the mathematical sets that we have seen in math courses. And dictionaries is a very special. So those are the data structures we're gonna talk about. Um, so basically, this is a collection which is ordered and changeable. So basically, if you think about this, if you think about string, I would say it's not exactly a list in the sense that whenever you have a string, then the elements of the string, the characters within the string are not mutable. Whatever you change will give you another string. Okay, so that's something pretty different from when you compare a string with a list, which is something that led to a confusion that we had earlier. So basically, whatever operation that you do to a string, okay, it will produce a new copy of the string, which is returnable as a functional value. Okay, but in general, whatever that you do to elements of the string of a list, that's always doable. You can always change the elements of the list, and it allows duplicate numbers, just like the when you have that list of, let's say, 1117, and you do permutation, that's a valid list, and you are able to construct reasonable permutations. But now tuples is a little bit different. So tuple is uh, sort of like a vector. Okay, so in linear algebra, they use round brackets to indicate a tuple. So that's ordered and unchangeable. Okay, so that's pretty interesting. So basically, you are not able to update the element of a tuple. Okay. It also allows duplicate elements. And then when you talk about the set, then that's the mathematical set that we are talking about. So every element appears once. Okay, it's either in the set or not in the set. And there's no order. Okay, so it's unordered and unindexed. So it will not allow duplicate elements. And indeed, in the set, the order doesn't matter. Okay, so you only worry about the inclusion. Right? Finally, we have the dictionary, which is unordered, just like the set. Um, the elements, however, here they are changeable, okay, and they're indexed. But the index with keys, okay, so that's pretty special. So in a set, there's no order, so there's no index, okay. The dictionary serves as sort of like a set, but they don't they use more general indices. So like the list and the tuples, they use integers from 0 up to the cardinality -1, okay, to be the indices. But then later we're gonna talk about the indices of the dictionary, which could be anything, okay, which could be strings. And it will not allow duplicate members. So dictionary turns out to be very important in data science. All right. Okay, so all right, so okay, we are now looking at we're looking at here. Okay, so the lists are defined using square brackets. We have seen append. I think we have seen append. and insert. So yeah, let's take a look. So eventually, if you have a list of 4 terms, statistics, algebra, topology, and statistics, if you append analysis, it will be the string analysis at the end of your current list, which will be here. So yeah, well, it's being executed, but the outputs are already here. And then, okay, that's always at the end. And then if you think about the insert, you will be able to get to a certain index to put your element. So here, if you want to put it the index 1 location, it's going to be where? It's going to be, so statistics right here. So this right here is the 0 index, okay? So if you, so the index 1 is actually at the place of algebra. So if you insert at the index 1, then the following elements will be index 2, 3, or and so on and so forth. So that's the insert. And then here, instead of writing your own loop, I would say reverse is an operation. Okay, it's a method that's commonly utilized. So you can also reverse the order of the list. But remember, it's a method. Okay, it's not a function. So let's try that. So print. Just to see if it it gives any error here. So here we're printing 3 things. Okay, if you do a dot reverse, actually it's none. So sort of saying, okay, reverse is not really a function. The method that you apply only affects the original data. Okay, so now the printed A will be indeed the reverse of the original A list. Okay, so analysis, statistics, all the way to the top. But then sort is also doing a similar thing. Okay, so when you do the sort, you're just doing the alphabetical order. Okay, so basically it's AL, AN, CO, ST. Now statistic appears twice, so they're there, and then T. So it's gonna be alphabetic. Yes.
Silly question. When you say function and method, what is the difference for that part you just said?
Yeah, very good question. Very important. So when we talk about the function, we basically mean that, okay, when you do this, you sort of have a returned output. So this is always this is the way that you apply a method. Let's try this to see if it does anything special or not. So yeah, it's not even a function. So we don't really have this as a function. So the point here is, okay, I have an operation. A dot reverse actually just directly acts on the data itself. So now you print A, it will give you a completely different list. Okay. And here, this doesn't give you anything reasonable. So there's a none type. So basically that just tells you, okay, this is not really a function. Yeah, a function is something like, okay, define the function name with the input and return something. So here it doesn't return anything because that's the none, right? So that's not a function. Methods are usually not functions. So you don't really have the name of that operation, then with bracket, then put in inputs. So you don't really have inputs. And for the sort is similar. So a dot sort is saying, okay, I'm gonna use the method sort to sort my list, and you will get the alphabetical ordering of the list.
Words and numbers in your list.
Let's try that. So there can be mixtures with 1, 2. Okay, so let's try that. Okay, so there's some problem with sort. So now integer and strings cannot be really sorted. So let's try the strings. So the strings should be able to sort. Yeah, so now the numbers go before the letters. Okay, so just like the computer program would do for, let's say, Windows. Yeah. So yeah, there's always a way that you can do alphabetic sorting for strings, but for numbers, no. Just this had to be somehow compatible. And you see the functions are well written so that okay, whenever there's something illegal, they just pop it up. Yeah.
Going back to the like conversation about methods. So the collection data types, those are all predefined methods that then you apply to some string.
You are talking about data types.
Yep.
Um, that's a very good question. So I would say list, tuple, set, dictionary, they are sort of like a high level thing that's they are different objects or different data structure that you are allowed to use them to store your data. Um, they are different from the methods in that now you have so you have certain features that can act on those objects. So those methods are basically what actions that you can do to the data structure that you have. So yeah, this is like the terms in object oriented programming, but we're gonna get deeper into that subject in at the end of lecture 7 and the whole lecture 8. Yeah, so we're gonna touch a little bit on those things. So to manipulate your data structure, so especially dictionary, okay, so let's say you want to sort of like say model a car, right? There's many different features and different data that you can associate to your car. So like the brand, the make, well the year and many other features. So that dictionary is basically the way that you collect the data, and then the operations are basically they sort of write up many kinds of things that you can do to the data. It's just like reverse the list.
Okay.
So yeah, so that's they are so common that they write it and then make it really efficient so you don't have to reproduce.
Okay.
Yeah, but that's the distinction that I see in my perspective.
All right, thank you.
Yeah, this is a very good question because in general, at the end of the day, you would want to go back and ask, okay, what's essentially the difference? So the data structures, they are critical. Okay, they are the way that you store your data. Okay, but then how to manipulate? These are the methods directly acting on the data structure. Right. Now more operations. So remove and pop. Okay, so these are really important. So so basically remove removes one time, okay, of the element statistics in the list. So let's see. So let's see how many statistics are there. We have 2, right? So how does it remove? So so if you think about the data we have now currently, what's A? A is actually the one at the end. Okay, so let's not sort. Let's just remove the sort so that the list is a little bit more interesting. Okay, so now we have statistics here and statistics here, right? So let's try removing statistic and see what happens. So the original data is this, okay? So now you see if I remove statistics, this string, it actually removes the first that comes up. So now this one is gone. So and then what happens to pop? So a pop 2 is actually saying, okay, I look for now the output, and I'm looking for the index 2. So 0, 1, 2, and I extract this element, and then make it disappear in my original data. So every time the original list A is modified, okay? And now here, this is pretty interesting. So let me get a B equals this, and I also print B. So okay, so yeah, it did it again. Okay, so it popped another element. Oh, it also removed the statistics again. Okay, so there's no statistics anymore. So yeah, well, you do realize that we are able to extract an element, which is the index 2, so 0, 1, 2, the topology is extracted. So in this pop operation, this is something you can utilize for writing your permutation function. Okay, so earlier you said, okay, I have an element, I get everything before, everything after, and then I form a sublist, right? So that operation can be replaced by using pop. Okay, so but remember, the pop is modifying your original data. So you would want to, so basically for, let's say doing permutation, let's say you have a list A, right? You make a copy, you make a deep copy of A, which is like, let's say a temp. And then you can pop whatever element that you want in the temporary list. And then for that popped element, okay, so for the one that you extracted, that can be stored as something, let's say B equal to. So here, this is really special. So it does two things. So it stores, it outputs the popped element and removes it from the data. Okay, so that's pretty special. All right, so those are the operations that are really common. Yes.
So for pop specifically, could you like add a comma and ask it to do like remove two at once, or would you have to do a new line? Like another pop in order to remove if you want to remove multiple things.
I think this only removing one and extracting one element. But let's try. So now here we can, but the list is getting shorter. Okay, so let's see. Let's say from 2 to 4. So meaning index 2 and 3. So yeah, well, it doesn't allow you to do so.
A copy that and then
Yeah, so it just allow you to give a number there. So invalid syntax. So you cannot really do this. Two. So it does again. Okay. Wait.
More elements it removes in that index.
Also now there's no, so wait.
Yes.
that's fine. You multiply it,
Well, only if you want to keep an moving element that's
the
in
second
that.
element.
Yeah,
We chunk it in index.
right.
So let me try that again. So
Two more.
How were they removed? 3 and 4.
It's probably because it doesn't know which one would do first, because then you're creating, it doesn't do both at once. It has to do one first, and that's why it doesn't.
It's like, it's only removing one element at a time, but it keeps removing the index
there's-
two element.
Well, you have
Yeah.
a whole new list, and it's like, well, how do I know?
Well, can you multiply the same thing twice?
you mean this line?
Yeah, and each time you remove the second element from the new list.
Oh, yeah, you can do that. It just does it twice.
Well, you don't even have to print it a second time, just the more times you just run it again and it removes an element again.
We don't really need this. So yeah, so let's just try that. So yeah. So wait.
You just have it printing A twice. And
That's yeah. Let's see. We removed the zero, 1, and 2. So we move this, and then remove this. So that's what resulted. Yeah. So yeah, every time it does, it just does it once. So
No, but can I say 2 multiplied by,
A prop 2.
yeah,
let's try that. Let me comment this off. Let me run that again so that the data is a little bit longer. I think it works.
it's printing twice.
No.
A set the index 2 element because 2 times a removed element, well, the element's been removed, so you're basically doing like 2 times 0.
Let me see what this gives me. So I actually haven't tried this before. So yeah, it's something always you can try. Just whether it gives you a bug or not. Yeah, let me just copy this so that it doesn't. I don't need to run it every time. Print B. Yeah. So yeah, it runs it once and then it just returns 2 copies of that and then stopped. Yeah. So yeah, well, that's sort of like the
Looping help for it.
yeah. If you want to remove once a time, then yeah, you can do a loop. But then what this says is sort of intuitive because that's a dot pop is returning you a value, okay, returning you an element of the string. So you have it should be an element of the list, which is string. So you 2 times the string actually is a valid operation. So that's 2 copies of that, and then yeah. So that's good. Okay, so now we look at lists of lists, which is multi-dimensional lists. So we have seen from that homework question. Okay, we have a list of uh different lists, right? You are able to take the average of those sublists. So in fact, you can do this kind of nesting. It's just you can. It's just it's gonna be complicated. Okay, so basically, essentially, you're saying, okay, I have when you have a list, it's just gonna be sort of like a vector. Now you have a list of lists is sort of like a matrix, right? You have a 2-dimensional object, and if you have one more nesting, it's gonna be 3-dimensional object, which is sort of like a tensor, and just yeah, you can do it. It's just you need to be careful, so that everything is well defined. Other than that, you are fine. So we have the first sublist was 1, 2. The second one is 3, 4. The third one is 5, 6. So now if you look on the high level, A of 0, okay, extracting the 0th element of my grand list. That's actually the index 0 right there. That's the first, well, it's the 0 index. The list with index 0, okay, sublist with index 0. And then if you go A1, it's actually this one, all right? But now what about A01? So that's actually the index 1 element of my A bracket 0 list. So it's actually index. So this one is my A0. So the index 1 is that 2. All right, so that's there. And then if you want to modify the element, that's fine. Okay, so you just say A01 equal to 3. That's basically pointing towards this 2 to replace it with this list. Right. So just need to be careful. So whenever the index runs out, then you will get an error. But besides that, everything is fine. Yeah.
For the second print statement, A bracket 0 bracket 1,
Yes.
does it produce 2 because they're two independent events? Like, if you look at it like logically,
Mm,
instead of it producing,
in terms of logic, I would say they are actually conditioned. So this element, the output relies on the list that contains it. Okay. So you first need to determine the outer layer. That's sort of a sense.
but couldn't you technically take the first list within the 3 lists? That's 1 and 2. Doesn't it also have the value 0 and 1?
Right, indeed. But then it's really up to like the different lenses. Let's try 1 to 10, 12, and then we have 5, 6, 7. Then okay, the length of this is actually 4, right? So it's dependent on which list that you're looking at. Earlier you have 2 to 2, so here for so my point here is that now this index is really up to 0, 1, 2, 3 for the index for the list 0. For the list 1, you will have an upper bound of 1, 0, 1. For this one, it's a 0, 1, 2. So it's sort of really dependent on the data structure that you predetermine. So let's try something 3. Okay, so let's try that. So it should give you 12, right? And then if you change it, so that's really dependent on the data structure that you so that gives you this illegal, the index out of range.
Okay, so it's kind of like a conditional set by the first variable.
Exactly.
Composition of functions.
Yeah, so the following index is the index of the object that you, indeed you can say this is exactly a composition, but
Because it looks first at which list do you want to look at within the list, and then it looks like at the index of the element you want.
Yeah.
In that list you picked.
Yeah. So the first index tells you on the high level which composition I would go to, okay, which output I would pick. But now the output is the list. So then you specify with the next index how to specify the index for that particular list. And it can go on. So in the nodes I would write, you can have A of bracket, 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 bracket. It can be a sequence of brackets, really up to the way that you define your data structure. However, I would say the downside is that indeed it allows you the freedom of nesting, but the downside is that you need to be very careful about the definition so that everything is still eventually legal. But at this point, indeed, it's not universal, so the latter is really dependent on the former, so it's kind of a conditional.
Okay, thank you.
Yeah, this is actually a very good question that you asked, and then we can try to explore. So now let's change back to 0, 1. So that indeed the lists can be changed. Okay, so the elements we can mutate. So that the 2 becomes a 3 right here. Right, so you can assign elements to it. So that's ordered list which has elements that you can change. Right? Tuples, they are brackets, round brackets, ordered immutable. So append will not be able to apply to a tuple. Basically, you define, let's say, 4 tuple, then you cannot make it longer. So that's a problem here. So 2, 3, 4 print T2, which is saying, okay, I'm looking at the index 0, 1, 2. So that's the 4 there. So if you try to assign a value to it, you will get an error which says tuple does not support assignment. Okay. And then if you append, it just said does not have attribute append. So yeah, well, I think in Python they call it attribute. So in the sense of objective-oriented programming. But here, let's just call it the method. Right, so that's what's special about tuple. So unfortunately, you will not. So once it's determined, which is fortunate in a sense. So it's pure data. All right. So now one thing special is that whenever you have a one element tuple, it has to be with a comma. Okay. So yeah, that's just what it says. If you do not have the comma, then it actually reads as just a number, just as the value inside the bracket, nothing else. So R here is actually what? It's actually a list of a list with element 1. So that's think about it. A bracket with nothing is actually the empty list. Okay, so you have one there that's saying, okay, I'm having a one element within the list. But now for s equal to 1 with the bracket, it doesn't give you anything. Okay, so it's just an integer, just like just there. Okay, so that's my s, which is just a 1. If you get a type, is actually the type of int. So the brackets here doesn't do anything. Okay, so you do need a comma there to specify the data structure. Okay, so now it's a tuple, right? So what's T? So okay, T is the okay, so let's try that. So here, you would be able to do the slicing and then add an element and then combine as a new excuse me, as a new tuple. Okay, so that's a little bit different from before. So this is something you can do to construct another tuple. All right. So think about this 2, 3, 4. So what you are doing here is, okay, I have a tuple which is 1. So I'm keeping 0, 1 as my indices, and then starting from index 2 all the way up. So that's my index 2, which is the 4 there. So here, essentially you are just reconstructing the entire tuple there, but you will not be able to append to make it longer. So that's kind of interesting. All right. So, and of course, you will not be able to assign new values to the tuple elements, but here indeed you can do this kind of slicing and combination. So that's good. Okay, sets. Now sets, they are traditional math kind of concept. We have no orders. So basically every element appears once. So it's mutable. So here we are able to do add and remove from a set. Okay, this is sort of like the opposite functionality of a tuple. So, however, we cannot get access to any given element since there's no indexing of the elements of the set. So here, to get the first entry, you would do a pop. So wait. And one thing to note is that different string will give you different excuse me, a different set will give you a different print. So it may not print as your data suggests. So you see we have three strings: algebra, topology, and analysis. Okay, so that's since it's non-ordered. So basically here we have two comments saying, okay, explain why this prints differently from the order above and explain the behavior of add operation. So you see we add statistics. So basically in computer, they do have a way to assign certain hashtags to each data that you have, but they are not necessarily in the alphabetical order or in the order that you already assign your data, which is something interesting. And pop always pops out the first element of that hash information instead of the original information. So let's see, algebra, topology. So statistics is okay. It's at the second place. So here there's no indices anymore. Okay, so and you pop algebra. Okay, so that's the first thing in the list. Excuse me, in the set. Well, in the computer, there is a sense of ordering, but you just cannot access it. It's sort of like a hidden thing that's not related to the problem. So
Statistics, algebra, and analysis.
what I can tell you is what they call it the hash table. So if you ever want to get more proficient in coding, then I think hash table is a data structure that's very important in some subsequential computer science courses. Eventually, let's say for certain problems that you want to avoid doing for loops and use a little bit more memory to speed up your computational performance, then hash table is something important in that aspect. So it uses a little bit more memory, but it's a trade-off. Okay, so you speed up the computation. Okay, using less of iterations, but giving more data. So let me just put the answer here so that you guys can Google. Okay, so this is what's called the hash table. So even though the data we don't have a explicit obvious index, but every element in the data will have a hash value in the table so that the computer can associate. So then in the hash table, it just appears that that's the order in terms of the hash table. So algebra is the first in the understanding of the computer, and then statistics is now added as the second element, and analysis is the third, and topology. So when it pops the one that's up front. So let's try something else. Let's try, I don't know. Optimization. So yeah, optimization appears here. But when you add statistics, it's here. And optimization comes at the third place. So which is just you don't really know what the program thinks. So now algebra, you see, it initially it has the I would say smaller hash table value, okay, hash value, but then it jumps to the fourth place. It's really up to how the computer would interpret the data. But yeah. But then indeed for at this stage, the analysis is the first element in the understanding of the computer. So then it pops that. So let me also add a B. So let B equals pop, and then let's print B. So just ensure that pop does what it supposed to do. Yeah, but fortunately, every time it runs, it's deterministic, so it doesn't randomly change. Okay, so every time, so wait. Yeah, optimization is the fourth place, and then the third, and then removing the first is going to be the second. So yeah, indeed, still, whenever it still pops an output, okay, which is analysis. Right? And this is actually a pretty good example. So algebra was first, and then all the way jumps to the second last, which is pretty weird. But it basically tells you the difference is that, okay, I include one more element, so the set is different. So basically, when you have a different set, then it's possible that they assign the hash tags differently for every element. Yeah, which doesn't make sense to you just by eyeballing, but that's what's behind the scene. That's what's called the hash table. Okay, so yeah, important in computer science data structure. Structure, but here let me put it in bold in capital D, because that's a course. Okay, so that's a course. But for us, if we only look at data science and we just think about the ways to manipulate data, then we don't really need that in-depth knowledge. Right. So that's good. Yes.
So is that something that varies between like individual computers, or does it depend on who made?
I think it's just up to Python. Yeah, it's just the language. And well, actually, as a reflection to your question, indeed, for different let me see, let's say for language C++, Windows machines and let's say CentOS machines and Unix machines, they actually perform a little bit differently in terms of computation. But that difference is actually a reflection of the architecture of CPU. So it's not really that the algorithms are doing different weird things. They are pretty deterministic. Even if you have random behaviors like random seeds. So the random variables, they have seeds. So essentially, they are not purely random out of nowhere. They just certain deterministic methods are sort of hidden like randomized behavior. But to answer your question there is the problem here is not really purely random. There's something fixed within the computer language. Okay. So yeah, these are questions that are very good, and if you are interested, make sure to explore, because those things you can indeed dig into certain aspects that are deeper, but are interesting. Okay, so setting for loop.
Other silly question I have
No
is
problem.
the difference between list and array.
Very good question. Lists can consist of the strings, integer, float, and boolean. So it can have all kinds of elements. But in terms of arrays, it's more related to linear algebraic packages like NumPy. So in arrays, you would have just data, just have floats.
Okay, so in array.
The list of numbers.
Needs to be the same data type.
Usually when you talk about arrays, it's just the floats. And you may have higher precisions of data depending on the needs. But when you talk about array, usually it's just linear algebraic stuff.
Okay.
Yeah.
But if I want to use stats on the list versus array, can I work with both? If the types considering list and array are both only integers, but then the length might vary or.
It's really application dependent, but for this you can do the legal operations that you have for data types, right? So strings can be added. Strings cannot be added with other numbers. So that's the only constraint. So basically, you want to define certain things with mixture data is totally fine, but make sure that you have compatible operations within your data. Yeah, string with string, number multiplying string is just repetition of string, so it's just the traditional stuff. Nothing new.
We're gonna talk about matrix later.
Later, yeah.
Oh,
So yeah, we will just go through the things up to the end of the semester. So it's just how much we are actually going to cover. So possibly like regressions or machine learning models, we may touch a little bit less on those, but focus more on the things building up towards those. But of course, when the plottings, they are the ones right after the objective oriented programming, which is like so that's lecture 8. So roughly lecture 9 or 10, we're gonna talk about the NumPy and plotting stuff. And then yeah, so yeah, well the further we go, a little bit more involved using packages. Yeah, but basically using different kinds of packages. Yeah. So for loops. So let's get down. So here, notice since we mentioned that the set is no index, right? So here, if you want to do the loop, you cannot really do the length of the set and then from 0 to that. So you cannot really write the for loop in that sense. You are writing it in this sense. It's going to be X in S. It's going to be basically enumerating every element. Okay, so this is a little bit new, but which is not too bad. And you see the order changed. Okay. Okay, more set operations. Okay, so there will be difference which returns a set containing the difference between two or more sets. So this traditional set difference that we have seen in the set theory. Okay, so it's like A minus B. So the things that are in A but not in B. Intersection, whether the two sets are disjoint or not. Okay, is whether the first set is a subset of the next or not. Is whether A is a superset of B or not. So things like those. Okay, symmetric difference. So when you talk about symmetric difference, is what is A minus B union B minus A. So things in A not in B, things in B not in A. So kind of that union. Okay, so when you have a set, you can union set. So those are the operations that are doable. Okay, when you have different sets. But those are the things that you can utilize, okay, and explore a little. Okay, dictionaries. Okay, so yeah, well, okay, very importantly, let's talk about this item and then we call it a day. So here, dictionaries are using curly brackets, okay, and colon. So colon is basically saying, okay, I have an input, I assign an output. Or you can say the key A is actually the index of my data value A, okay? Key B is my index for the value B, and just it goes on. So it's unordered. The elements are changeable. Okay, the things are changeable, and the index, but the index are the keys. Okay, so the things before the colons, the elements are separated by a comma. For example, here I have my car, which is a dictionary. We have the make associated to Ford. model says to Mustang. Year is 1964, which is an integer, right? So basically, my car is actually all the data that you associate the keys to the values, and then now the index is what? The index is make, model, and year, and which are not integers. Okay, so that's something very different but very powerful. All right, so I guess I'll see you guys on Wednesday.